Hi students, welcome to the very first H2 chemistry lecture on atomic structure and physical periodicity. Before I delve into the lecture proper, I thought I just want to bring you through how the lecture notes are being organized. Okay, so first of all, we have the topic number, so that's topic number 1. And then this is followed by the title, which is Atomic Structure and Physical Periodicity. Yeah, you can use this as a guide to help you in a revision because you have a total of about 23 topics which we will cover for the whole of the H2 chemistry curriculum. Okay, and the topic number as well as the title will also correspond to what we have in our Google Sites. And if your tutors have a Google Classroom for the class, the Google Classroom topic number will usually correspond to what you have in your lecture notes as well. Okay, and then right below you have the guiding questions. These guiding questions are usually questions which make you think about the topic in a deeper fashion before you begin revising the topics or before you begin reading through the topics. You might have answers to some of the questions, but most of them it will become clearer as you revise or you go through the topics via either reading through the notes or the lectures. Okay, so for example, the first bullet point, what makes up an atom? You will have answers to this based on your prior knowledge from either O levels or for your integrated program respective schools. However, are there more things that you need to know? So again, H2 probably covers the same amount of knowledge that you have already learned from secondary school, but if you want to go deeper, for example, beyond protons, neutrons, electrons, you know that they made up the atoms, and you know that atoms are indivisible. If you want to learn more, for example, you want to learn more about the fundamental particles, then feel free to study them on your own. Okay, so these are very interesting stuff which we normally will not cover in a lecture setting. Okay, and then of course, most importantly, the next part are your learning objectives or learning outcomes. We have written the learning objectives and learning outcomes in a fashion which corresponds to what you have in your syllabus documents. So for example, under topic 1 on atomic structure, we have 1A, B, C all the way to K, right? You notice? Okay, so let me move on to the syllabus documents. Okay, so this is a syllabus document. I'm just going to go straight to atomic structure. You'll notice that the learning outcomes corresponds directly. So this is topic number 1 on atomic structure. Okay, so you have A, B, C all the way until K. Okay, what is the advantage of having the learning outcomes on the cover page? It allows you to review them when you are doing your revisions. So for example, when you're doing your revision, right, before you read through your lecture notes, you might want to ask yourself, okay, so let me look at learning outcomes 1A. Am I able to identify and describe protons, neutrons, electrons in terms of their relative charges and relative masses? Yeah, so this is the thing you need to know in your curriculum. So if you are able to, on the top of your head, tell me what they are. For example, if you are able to tell me that, okay, protons have a charge of +1, neutrons 0, electrons -1, and the relative masses of protons and neutrons, if we assume that they have unit 1, electrons will be about 1/1840. If you have such knowledge, then that means that you have already fulfilled objective 1A. Then you can move on to review 1B and think about it. Are you able to deduce the behavior of beams of protons, neutrons, electrons in the electric field? So for example, if you are not able to, then you can go and review the relevant section from your lecture notes or review the relevant parts from your lecture videos. Okay, but you also notice that for this particular chapter on atomic structure and physical periodicity, we also include learning objective from the other topics in your syllabus documents. So for example, under chapter 5, okay, so let me move on to chapter 5 over here. So chapter 5 topic is actually on physical periodicity or periodic table. Yeah, so we took up 2 very specific objectives which we felt that it's better to be covered under atomic structure. So that is on A and B. Recognize variation in the electronic configuration across a period and down a group. Okay, so these are things which we took up because we realized that it is actually better taught under atomic structure. Okay, so under stoichiometry, we also took out 6a and 6c, so that you're able to define what is relative atomic, isotopic, molecular, formula mass, etc. So these are things which we thought that it's better to be covered under this chapter. We also took out 3 learning objectives from transition elements. Okay, so transition element is right at the back. Okay, so let me go to transition element over here. So this is the last topic you will learn in your whole of H2 chemistry curriculum. So you probably learn it in 2024 May. That is about 16 months from now. Yep. So we took up 3 of the objective, A, B, and C. Yeah. Again, same reasoning, because they are better covered under atomic structure. Okay. So after we go through them, you will understand why we have put them in this particular chapter. This is followed by some of the references. So if you are interested in finding out more, okay, you're just not too happy with the H2 curriculum alone, you want something more rigorous, yeah, feel free to look at them, especially on the references beyond A levels. So the first 2 are on A levels. If you wish to, you can move on to look at the chemistry, molecular nature of matter and changes by Martin Silberberg. Okay, we have a lot of copies of this text in our library, so please go and borrow them and look through them on your own. Okay, and of course by Messler and Thayer on Inorganic Chemistry 3rd edition. Yeah, so this is a very, very good textbook on inorganic chemistry, and it goes a lot into details. So for students who are especially interested in transition element, this is a go-to textbook. Okay, so I'm pretty much done with the introduction of the cover page. So now I will go into the lecture proper. Okay, but most of the things, or quite a number of the content in at least the first 2 sections of this chapter, you already know quite a bit of them, so I will not go into details. So for example, for 1.1, this is a background reading for you on the discovery of subatomic particles. Yeah, so if you're interested, you can go and look through the experiments by John Dalton on how he formulated the atomic theory, and also the pudding experiment by J.J. Thomson. So he actually proposed a model described atoms as negatively charged electrons embedded in a sphere of positive charge. Of course, all these are known to be incorrect, but at that point in time, these are very, very sophisticated or very, very important discoveries. Yeah, it is not until 1910 when Rutherford performed the alpha particle Goldthorpe experiment. Yeah, so this is the most famous one being performed, and that actually shows us a few things. So for example, that more than 99.9% of the atoms is made out of empty space. Okay, and the nucleus is just a very, very condensed and compact portion in the middle of the atom. Okay, of course there are more discoveries later on. For example, we know that they are being defined mathematically by some sophisticated equations, and how the electrons are actually at different energy levels, etc. So all these we will not go into details for H2, but if you are interested, you can read more about them. Okay, so we'll move on to 1.2, where we'll introduce you to the 3 subatomic particles, and I'm sure you have already known them from secondary school: electrons, protons, and neutrons. So over here, again, I will not go into details, except that this particular table 1 gives you a glimpse on learning objective 1A, which I described right at the beginning. Okay, like their relative charge as well as their relative mass. Okay, and do take note on how they are being written. Okay, so they are usually being written in this particular fashion, so you need to know what it means. So this is the elemental symbols. So for example, for carbon, it will be C. Okay, so it will be C. Then the one on the bottom left, okay, is what we call the proton number. So for example, carbon will be 6. Okay, so we'll write it over here, and then the top will be the nuclear number. So most the most common isotope of carbon is carbon-12 with 6 neutrons. Okay, so we'll put 12 over here. Yeah, so based on this, if we take the difference between the nucleon number and the proton number, you will get the number of electrons. Yeah, those of us who studied history, we know about the carbon-14 dating, right? So based on this, you will be able to find out the number of neutrons in carbon-14s. So that will be 8. Okay, yeah, so most of us already know most of these things, so I will not go into details. Of course, before I move into isotopes, I just want to kickstart your interest in a very interesting questions which a lot of students ask. Normally, the students ask at the back of their it's at the back of their mind, but usually they do not want to ask in a tutorial setting. Yeah, because they just take it to be gospel truth. Okay, so what is the thing we want to ask? We know that the nucleus contains protons and neutrons, and we know that neutrons do not have charges, so 0. Protons have +1 charge. Am I right? Yeah. So the questions that you might have in mind is then, why wouldn't the nucleus disintegrate on its own? Because like charges repel. That's what we learned under electricity or under charges in physics. Yeah. So you might be wondering why that is the case. So what you have not learned in secondary school and of course in JC is that there is another more powerful force holding the nucleus together that is known as the strong interaction, or some resources will call it the strong nuclear force. Okay, so there is a video, I'll put the link below, which you might be interested in going through on your own to understand more about this. And the video actually brings you through a very, very short introduction to quantum chromodynamics. Yeah, and that video talks about things like the quarks particles that made up protons and neutrons. Yeah, but I will just play a little bit of this video for you so that you roughly know what is going on, and I hope that this will kickstart some interests you have, so that on your own you will go on and discover more interesting chemistry phenomena. Okay, so I will now play the video.
Sponsored by Brilliant. Please sign up for free and support this channel at the link in the description. There are thought to be just 4 fundamental forces or interactions in nature. Gravity, which keeps you on the surface of Earth; the weak force, which is responsible for some kinds of radiation; electromagnetism, which is responsible for all chemistry; and the strong force, which keeps protons and neutrons tightly bound together in the nucleus of atoms. You're probably most familiar with gravity, which at the scale of the Earth, the solar system, and beyond, dominates the universe. But at the quantum scale, the other 3 forces dominate. For example, electromagnetism is a whopping 10 to the 37 times stronger than gravity. It's responsible for keeping the negatively charged electrons near the positively charged protons in atoms. So now you have to ask, since electromagnetism is so strong, then multiple protons in the nucleus of any atom, like helium and beyond, should repel each other very strongly. According to Coulomb's law, the 2 protons in a helium atom experience a repulsive force equal to about 90 newtons or 20 pounds. For something as small as a helium atom, this is a huge force. They should repel each other and fly apart instantly. The reason that these protons don't fly apart is because they're kept glued together by a force that is even stronger than electromagnetism, about 100 times stronger, called the strong nuclear force. It is the strongest force in the universe at the scale of the nucleus. This force is not simply the opposite of electromagnetism, but works through an entirely different mechanism, which, unlike chemistry, is typically not taught at the pre-college level. So most people are not familiar with it. I want to give you a glimpse of the fascinating world of quantum chromodynamics and show you exactly what goes on inside and in between protons and neutrons in the nucleus of atoms that keeps them so strongly glued together against the enormous repulsive force of electromagnetism. That's coming up right now.
Okay, I will stop the video. So if you are interested, please go and view it, and understand more about it. Those of us taking physics, you will probably not learn it in your physics curriculum, but of course, feel free to engage your physics teachers and maybe get them to help you understand or get some of the resources which you might need to find out more about quantum chromodynamics. Yeah, okay, and fundamental particles lah. So these are some of the things which are being discovered in the last 50-60 years, and of course a lot of research are still ongoing. Okay, so with that I'll move on to 1.3, that's on isotopes. You have learned about isotopes in secondary school, so we are just going to recap what an isotope is. So isotopes are atoms of an element that have the same proton number but different nucleon number. So that means that they have the same number of protons but different number of neutrons. An example here will be hydrogen. Okay, so hydrogen have 3 common isotopes: protium, deuterium, and tritium. So for protium, 0 neutron, deuterium 1 neutron, tritium 2 neutrons. You have heard from your teachers, perhaps in secondary school, they might have mentioned to you that it is the nucleon number that give rise to their nuclear property. So whether they are stable or not stable, whether they are going to emit radioactive particles or rays. Okay, it is the electronic configuration, which is also the center theme of this topic, that give rise to their chemical properties. Alright, so for example, carbon has 4 valence electrons, hydrogen has 1 valence electrons. Yeah, so inevitably they are different because the number of valence electrons kind of determine their chemical properties. Okay, so we're going to explore more about them later. Okay, so over here we give you an example of the different common isotopes of hydrogen, carbon, oxygen, and sulfur. Okay, and then of course here we also mentioned that they may be stable or unstable. Yeah, sometimes when we mean unstable, we don't really mean that they will disappear maybe tomorrow or the next second. Yeah, so for example, carbon-14, it has a half-life of 30 years. So that's like over 5,000 years. Yeah, so you might have heard of carbon-14 labeling, or even using like archaeologists to find out the amount of carbon-14 remaining to determine the age of the sample. Okay, yep. So over here we have a word example 1.1. Okay, so over here you're asked to complete the following tables with the number of protons, neutrons, and electrons of each particles. Yeah, so this is pretty straightforward because this basically tests you on whether you can read the symbols provided for you on the second column. Okay, so for example, silicon 14, the 14 here represents 14 protons. So this 14 here represents 14 protons. Yeah, so if you take the difference between 28 and 14, you will end up with 14 neutrons. Yeah, and because it is not charged, yeah, so the number of protons must be the same as the number of electrons. So number of electrons is also 14. Okay, then next example we have is gallium. Okay, so for gallium we have 31 protons, so 31 protons over here, and then we take the difference between 70 and 31, we end up with 39. So that means that gallium has 39 electrons, sorry, 39 neutrons. Okay, and because in this particular symbol, right, it has a 3+ charge, so that means that gallium atom loses 3 electrons. Yeah, so because it loses 3 electrons, the number of electrons remaining will be 31 minus 3, so that will be 28. Okay, and then we do the same thing for phosphorus, 3 minus. So again, 15 protons over here, so 15. So we have 15 protons. So the number of electrons, sorry, the number of neutrons here will be 31 minus 15, so that will be 16. Okay, and because there is a charge of minus 3, so the number of electrons here will be 15 plus 3. Okay, so 3 extra electrons comes from one of the species phosphorus react with. So in this case, the total number of electrons will be 18. Yeah, so this is how we go about working on this question. Okay, then next we have exercise 1.2 for you to work on. So if you wish, you can just stop the video and then after you have worked on it, then you can just continue the video and then look out for the explanation. Okay, so again we have particle P, Q, and R. Okay, so the question is give the symbols of the element showing the nuclear number and charges of the following 3 particles in the last column. Okay, so you notice that they are not the particles written, there is no charge being written on them. Yeah, so the particle can mean simply an atom, it can mean a cation or an anion. A cation is a positively charged species. Okay, in case you forgot, anion negatively charged species. Okay, so the first thing we look at is the number of protons. Okay, so it's 6 protons. So for 6 protons, we need to look at our periodic table. So you can just, if you cannot remember, of course, just go to your periodic table. So over here, so this will be carbon. Okay, so we'll write carbon over here. Okay, so we can do the same for everything. So 7 protons, 8 protons. So we just look at the periodic table. That will be nitrogen and oxygen. So this will be nitrogen and oxygen. So again, we can write 6, 7, and 8 over here. Okay, then the number of neutrons for particle P is 8, so 8 plus 6, that's 14. So we'll just write it here, and then 7 plus 7 is 14, and then 7 plus 8 is 15. Okay, we'll just write them in. Then the number of electrons for P is the same as number of protons, so the species is neutral, so we'll just leave it as it is. For Q, the number of electrons is 10. That is 3 more than the number of protons, so you will have a total charge of 3 minus, so that's minus 3. Okay, then for R, number of electrons is 7, so 1 short of from 8, so the charge will be plus 1. Okay, we'll just write it as plus. Normally for plus 1 and minus 1, we don't write the 1. Okay, just remember. For B, use the data booklet to identify which are not the usual isotopes of the elements concerned. Okay, so how can we identify which of them are not the usual isotopes? First, we need to look at the periodic table. Okay, so we'll move on to the periodic table over here. So for the periodic table, the relative, the atomic mass is given to us 12.0 for carbon. Okay, nitrogen 14.0, oxygen 16.0. So we'll just write it at the side over here. Okay, so just for us to keep in view, so 12.0, 14.0, and 16.0. Okay, you'll notice that for particle P, right, the nuclear number is 14, it's not 12. So this is not the common isotope for carbon. Okay, so I'll just put a star over here. So P is not a common isotope of carbon. You'll notice that for Q, the nuclear number is the same as the one given in the periodic table. So this is common isotope. For R, 15 is given to us. That's a nuclear number, but the common isotope has close to 16.0 as nuclear number. So this is also not a common isotope. So I'll put a star over here. Right, next we'll move on to exercise 1.3 as a work example. So over here we have 1999, Russian chemists claim to be the first to identify atoms of a new element of proton number 144. This was produced by bombarding atoms of plutonium, okay, with atoms of an isotope of group 2 element X. So we know that group 2 is alkaline earth metal. Okay, so X must be an alkaline earth metal. If we look at what we have over here, it could be beryllium, magnesium, calcium, strontium, barium, or radium. Okay, then the reaction takes place as follow. Okay, so we know that the top number, for our case here, 244 and 289, they represent the nuclear number, and then the number at the bottom, 94 and 114 respectively, they represent the proton number. Okay, so the question requires us to identify the nature of X. So what exactly is X? So therefore, the only important thing we need to do here is to identify the proton number. Okay, so therefore, based on conservation of mass, all we need to do is just to take a difference between 114 and 94, and then we should end up with 20 for X. So we'll just go to the periodic table, look for atomic number 20. Okay, so this will be calcium. Okay, so calcium is therefore the answer. Okay, some of you might be wondering, what about the nuclear number? How can we determine the nuclear number? Okay, so the nuclear number, if you want to determine, you can just let the nuclear number be A. for x. So based on conservation of mass, 244 plus A is equals to 289 plus 3. Not to forget, we have 3 neutrons being ejected out. So this is actually 292. Okay, so therefore A is equals to 292 minus 244. Okay, so if you just do a quick calculation, you end up with 48. Okay, so A is therefore 48. Yeah, but this is not required by this question, because this question is MCQ. Yeah, so you just need to choose the best response. Okay, yep. Then next we'll move on to section 1.4, ions and deflection of charged particles. This is new, so this is a bit different from what you learn in secondary school, because in secondary school you do not need to do any of these calculations. Okay, so negatively charged ions has more electrons than protons, so it's represented as it is. Okay, so I don't think I need to go into details. So negatively charged ions are called anions, positively charged ions are called cations. Okay, and they are being deflected by the electric field. So electrons or negatively charged ions will be deflected towards the positively charged plates. Protons or positively charged cations will be deflected towards the negatively charged plates. So neutrons will not be affected. Yeah. So over here, question is in figure 5, why is theta 1 bigger than theta 2? Okay. Yeah. So of course the answer is given to you. This is due to the mass. Okay. The electrons has a lower mass, so it is deflected to a greater extent. This idea is based on this general formula. So do take note of this. The angle of deflection theta, right, is directly proportional to the charge, but inversely proportional to the mass. Do take note of one very, very important details here. Sometimes students will forget. This is proportional. Yeah, so there is a proportionality constant that is not told to you. Okay, that is unique to the system. So theta is actually equals to a proportionality constant, say A Q over M. Yeah, when you perform your calculation, do not anyhow use equal. If it's proportional, please take that into consideration. Okay, yep. Then we have exercise 1.4 as a work example. So with this, I will bring you through the thought process. Okay, so in a particular experimental setup, protons are deflected through an angle of 15 degrees. Okay, do take note of this. Protons deflected through an angle of 15 degrees. Maybe I can write the formula here. So theta is directly proportional to the charge, inversely proportional to the mass. Okay, so if I'm going to write it for protons, so for protons, the angle of deflection is 15. Okay, so 15 directly proportional. The mass of proton is 1, and the charge is plus 1 as well. So this is plus 1 over 1. Okay, assuming an identical set of experimental condition. Okay, so this is actually trying to tell you that the proportionality constant will be cancelled out if you divide them. Okay, by what angles will the following particles be deflected? Okay, so over here we have the species. Okay, then D minus. Okay, so we have a deuterium D minus over here. Okay, so do take this into consideration. So I'm just going to draw a border around it, and then I change to another color ink. I will change to orange. Okay, so we have deuterium. So deuterium has double the mass. Okay, so therefore, right, for deuterium, let's say it's A, right? Let's say we don't know the angle of deflection, we let it be A. So A will be proportional, in this case, to minus 1 over 2. Okay, so what we can do over here will be, we will divide A, we'll divide A by 15, so A over 15. In this case, the proportionality constant will be cancelled away. Okay, so in this case, this will be equal. So now we can put an equal sign. Minus 1 over 2 divide by plus 1 over 1. Okay, so therefore A is equals to minus 7.5 degrees. Okay, we just take minus half times 15. So therefore, this is the angle of deflection that we get over here. Okay, what about tritium? Tritium has 3 times the mass. Okay, so for tritium, same thought process. Maybe I can change to red. Okay, so I will just use an eraser. So for for tritium, it has a +1 charge, so just cancel this, and then we will cancel this as well. Okay, so it's +1 charge, +1 divide by 3. Okay, and then we let it be A as well. Okay, so in this case, we're going to just cancel this. This will be +1 over 3. Okay, and then of course now the angle is not 7.5 degrees. It's actually plus 5.0 degrees. Okay, so that's how we get this particular answer. Okay, what about helium-2 plus? So again, the same thought process. For helium-2 plus, what we do here is, again, I'm just going to cancel this. Okay, so everything we cancel. I'm going to change to green. Okay, oh sorry, green we have used it, so maybe I'll change to blue. Okay, so for helium, that will be +2 over 4, that's the mass number, so this is +2 over 4. Yeah, so this is half again, so plus half times 15 degrees, so that's plus 7.5 degrees. Okay, so do take note of this. That's how we get plus 7.5 degrees. Note that the sign is also important, okay, because that determines whether it deflects towards positive or negative plates or in opposite directions. Okay, so that's exercise 1.4 as a work example. We'll move on to the next part, exercise 1.5. Okay, again, similar to what was mentioned for exercise 1.2, you might want to pause the video now so that you can work on your own, and then after you are done, just continue playing the video. Okay, so for exercise 1.5, we have a plasma. Okay, so it's a gaseous mixture in which the atoms have been completely stripped of their electrons, leaving bare nuclei. Because of possible use in controlled nuclear fusion reactions, plasma behavior has been intensively studied. So when passed through two plates carrying a certain electric charge, 1H and 4 helium nuclei are deflected. Okay, so again, you are given the angle. This is the angle of deflection, of 1H and 4 helium respectively. Give reasons for your answers, such as the polarity of plate A. Yep, because both of them deflect towards A, and it's mentioned that the plasma is a gaseous mixture in which the atoms are completely stripped of their electrons. So that means that the particles are positively charged. Yeah, so because of that, the polarity of plate A must be negative. Okay, so just basing on this logic that the plasma is a gaseous mixture in which the atoms have been completely stripped of their electrons. Yeah, so that means that they are positively charged. Okay, yep. So for part 2, why 1H is deflected twice as much as 4 helium. Okay, so in this case, we have to look at the mass number. Okay, shall we do that? Yeah. So in this case, for 1H, the angle of deflection is directly proportional to the charge. So in this case, +1, and inversely proportional to the mass. Okay, so the mass of hydrogen, again, is 1. Okay, now for 4 helium, okay, so theta here is directly proportional to the charge. So helium has 2 electrons, so that's +2. Okay, however, the proton number of helium is 4. Okay, so because it's 4, so divide by 4. Yeah, so therefore, if you notice, in terms of magnitudes, hydrogen is double that of helium. So therefore, I expect 1H to deflect twice as much as that of helium. Okay, so we can easily use this explanation to support our argument. Okay, so remember that fundamentally, right, this equation is very important. Yeah, so you might want to learn how to use this equation well. Yeah, this is one of the few equations you have for atomic structure. Yeah, so it's a very simple equation to remember. You don't need to memorize it by heart. You just need to know that the angle of deflection is directly proportional to the charge, inversely proportional to the mass. I think that will be more than sufficient. Okay, and then the angle of deflection of 2H nuclei and 3 hydrogen nuclei. Okay, so we can easily do that we can easily do that calculation because we are required to calculate to 1 decimal place. Okay, so for 2H nuclei, so we can simply make use of hydrogen. Okay, can we do that? Yep. So we'll make use of hydrogen. Okay, so in this case, again we let 2H deflection be A, for example. Okay, can we do that? Yep. So in this case, we have 4 over A. Okay, 4 is the angle of deflection of 1H. Okay, so it's over here. Okay, so this is equals to plus 1 over 1 divide by what about A here? So A will be plus 1 over 2. Okay, yep. And then we can shift them around. Okay, so we can shift A to the other side. So therefore A is equals to 2 degrees. Okay, so we can do that quite easily. Or if you can easily tell that, oh, it's double the mass and it's the same proton, then therefore it's 4 divided by 2. You can do that as well if you wish to. Okay, yep. Then next we look at 3 helium. So again, we let it be B. Okay, so in this case, we can do B divided by the helium. Helium above is 2 degrees, so 2. Okay, so this is equals to plus 2 over 3 divided by plus 2 over 4. Okay, so therefore from here, B is equals to, we can cancel this. That's 4/3 times 2. Okay, so we will be able to get, let's punch the calculator. So that's 8 divided by 3. Okay, so let me find the calculator. 8 divided by 3. So we will get 2.7 degrees. Okay, so we can get to 2.7 degrees quite easily. Yep. Okay, so that's how exercise 1.4 can be performed, and I hope you have solved it as easily as how I've solved it. Yeah, simply by basing on the Q to M ratio, or just remember that angle of deflection is directly proportional to the charge, inversely proportional to the mass. Okay, next we'll move on to section 2. So for section 2 is on quantifying the masses of atoms. Okay, so this is quite important, but I am aware that most of you will have learned most of these things, if not all of these parts in section 2 in secondary school. Okay, we need to understand the definitions of relative atomic mass. This is often asked to your senior, or even for your promotional exam, or even your seniors common test, or a preliminary exam, even A levels, but most of them cannot really answer this question. Okay, so we call this the relative mass. We call this relative mass the relative atomic mass of an atom. Okay, yeah. Why is that the case? Because they are measured against a unit, a well-defined unit known as carbon-12. Yeah, so carbon-12 is the element that we use as a reference point. Okay, and of course carbon-12 is the most abundant isotope of carbon. So the definition for relative atomic mass will be, we need to remember that you write it as AR. The R is a subscript. Okay, so it's the average mass of one atom to 1/12 the mass of one atom of carbon-12. Do you know why is it 1/12? Because that is what we call the atomic mass unit. But atomic mass unit is not exactly in your curriculum. Yeah, so we assume that carbon-12 has 12 mass units, so 1/12 of it. So that is the reference. Yeah, so remember this is the average mass of one atom of an element, okay, to that of 1/12 the mass of one atom of carbon-12. Okay, so this is very, very crucial. Why is it average? Why is average being used here? Yeah, because we take into consideration the relative abundance of all the possible isotopes of that element. Again, all positive isotopes. Of course, there are some not yet being discovered, but when it's discovered, then the values will change slightly. Okay, yeah. So again, sometimes we need to deal with relative isotopic mass. So again, mass of one atom of an isotope of an element. So you notice that this is very specific to isotopes. So because it's very specific to isotope, here is the mass of one atom. Yeah, but for relative atomic mass, is the average mass of one atom. You notice that there is a slight difference in the way it's being defined. Yeah, that's because of the nature of the term being used. Okay, what about the relative abundance of isotopes? Yeah, so again, it's a mixture that is unknown to us, but you need to know some common ones. So for example, chlorine, we have chlorine 35 and chlorine 37. Okay, so the natural abundance is about 3 to 1. So we have 75% chlorine 35, 25% chlorine 37. That is why the relative atomic mass of chlorine, right, is 35.5. It's closer to 35 rather than 37. Yeah, okay. Yeah, so over here, there is a sample calculation being done for you to determine the relative atomic mass, okay, of chlorine. We have an example 2.1 as a work example. So over here, the relative atomic mass of borons, which consists of the isotope 10 boron, boron 10 and boron 11 is 10.8. What is the percentage of boron 11 in the isotopic mixture? Okay, so over here, there are of course several methods you can do. So for example, you can let the percentage of boron 10 be say A, and then therefore the percentage of boron 11 will be 100% minus A. Okay, you can do that. And of course, for this particular question, they let A be the relative abundance of boron 11. You can do that as well. Yeah, so again, simple mathematics over here. So so what you have would be 11A plus 1 minus A, 10 is equals to 10.8. You have one equation, one unknown. Yeah, so you can easily determine it to be 0.8. Yeah, so the relative abundance will be 80%. Okay, so this can be done quite easily, right? Okay, so next, we'll do exercise 2.2. So we have 5 isotopes of krypton occur in the following abundances. So 2, 12, 12, 57, and 17. Use these values to calculate a value. Okay, to calculate to 1 dp the AR of atmospheric krypton. Okay, so first of all, we need to ensure that everything adds up to hundreds. Okay, so that 2 plus 12 is 14, 14 plus 12 is 26, 26 plus 57 is 83, 83 plus 17 is 100%. So okay, so everything is accounted for. Okay, so we can easily do the calculation over here. So the AR will then be equals to 80 multiplied by 0.02 plus 82 multiplied by 0.12 plus 83 multiplied by 0.12 plus 84 multiplied by 0.57 plus 86 multiplied by 0.17. Okay, so punch the calculator. Let me take my calculator out. Okay, you should get 83.9. Okay, so that's the AR to 1 dp. So do make sure that in the case of assessment, right, read the question carefully. Yeah, because we will ask you to write out the number to a specific decimal place or a specific number of significant figures. Okay, yep. Next, the next question we will deal with is actually question 2 of exercise 2.2. So over here we have naturally occurring gallium. It's a mixture of 2 isotopes, gallium-69 and gallium-71. Use this information together with data booklet to calculate the percentage abundance of each isotope. Okay, so we will need the data booklet. So when we go to the data booklet, over here gallium 69.7 for the relative atomic mass. Okay, yeah, so we're supposed to calculate the percentage abundance of each isotope. So again, we use the same logic. So we let the percentage of this be A. So that will be 69A plus 1 minus A, 71, okay, equals to 69.7. Okay, so we'll solve for A. Okay, solve for A. Now we take the calculator, we punch, we should get 0.65. Okay, so therefore the percentage of gallium 69 is 65.0%. Okay, then the percentage of gallium 71 is therefore 35.0%. Okay, that's it. Right, we'll move on to the next section, which is a little bit more exciting. That is on electronic configuration, or as the title suggests, the arrangement of the electrons. Before I discuss section 3, I thought that it would be timely for me to just share with everyone that for H2 Chem, we are only discussing this on the surface. We are not going into the in-depth understanding of the Schrödinger equation. We are not going into the Born-Oppenheimer approximation, or even things like the Heisenberg uncertainty principle. Or we are not even talking about quarks or this in order to have a more fundamental understanding on why things are like this. Okay, I mean, why are the facts like this? Yeah, so if you really want to go into the nitty-gritties, you might want to read up a bit more on your own, especially on the 4 quantum numbers that define the so-called position of the electrons. Okay, because later on you're going to learn something called Hund's rule, and then Hund's rule has a more sophisticated definition based on the 4 quantum numbers. Okay, but again, for H2 wise, we'll not go into that. Okay, yeah. So I'm just going to go straight in. Principal quantum shell. This is something you're very familiar with from secondary school. Yeah, basically, you can tell the principal quantum number by simply looking at the periods. Okay, so for example, so let me just erase this first. So for example, in period 1, the maximum number of the maximum principal quantum number will be 1. Yeah, so that will be the first and only shell, and that will be the valence shell as well. Okay, for period 2, right, there is a maximum number of principal quantum number 2. So you can principal quantum number 1 and 2. Yeah, so principal quantum number 2 will be the valence shell. It is a valence shell from what you have learned in secondary school. Okay, so for example, I just illustrate it with an example. For example, for boron, for borons, the electronic configuration in secondary school, we'll write it as 2, 3. Okay, so the second one is the total number of electrons in the second principal quantum shell. The first number is the total number of electrons in the first principal quantum shell. Yeah, so in secondary school, most of you learn them as writing electronic configuration in separate principal quantum shell, and you separate them by a comma. Yeah, the difference between now and JC, or between secondary school and JC, is that you will write electronic configuration in a slightly different format. Yeah, so later on we'll elaborate. Okay, yeah, so basically principal quantum number is not something you are not familiar with. Okay, so let's say we have a third period atom. The third principal quantum number will be the valence shell, and principal quantum number 1 and 2 will be the inner quantum shell. Okay, there is a formula which is given to you even in secondary school, 2n squared, that represents the total number of electrons that principal quantum shell can take, but you do not need to memorize it, because you can easily derive the maximum by simply looking at the number of elements across the periods. Okay, what is interesting would be section 3.2, which is on subshells. This is quite different from what you have learned in secondary school, so therefore it will be good for you to pay a little bit of attention on this. Yeah, so each principal quantum shell can be divided into one or more subshells, or we call it sub-energy levels. Yeah, so what is pretty straightforward is that the number of subshells correspond to the principal quantum number. So for example, principal quantum number 1, there is only 1 subshell. Principal quantum number 2, there's 2 subshells. Okay, and we give each subshell a letter representation. Yeah, so the first subshell will be denoted as S. Okay, the Then after that, for example, for principal quantum number 2, there's a total of 2 subshells. Yeah, so out of the 2 subshell, the first one is denoted as S again, the second one as P. Okay, and how do we differentiate the 2S from principal quantum number 1 and principal quantum number 2? So we add the principal quantum number in front. So if we are looking at 2S, we'll write a 2 in front of the S. Looking at 1S, we'll write a 1 in front of the S. Okay, yeah. And then if you read up more, you will notice that the subshells, the type of subshells is defined as what we call the angular momentum quantum number, and that actually gives you the shapes, the shape of the subshell. Okay, so that is something which might be a little bit different from what you learn in secondary school if you did not explore beyond what you have learned. Okay, yeah, so that is something you might need to pay attention to, and in terms of drawing, we'll learn how to draw them later on. Okay, and of course, each subshell will be made up of orbitals. Okay, we call them atomic orbitals. Yeah, so you can see from here that for principal, let's say for principal quantum number 2, okay, there is a total of 2 subshells, 2 types of subshells. Okay, S and P. Yeah. So if you look at the above, the total number of electrons that is possible for principal quantum number 2 is 8. So the 8 electrons will be distributed between the 2s and the 2p subshells. Okay, yeah. And over here, you will also learn later on that each subshells has a different number of atomic orbitals. Yeah, and each orbital, the total number of electrons that can occupy the orbitals is 2. Yeah, you need to remember this. Yeah, each orbital only 2 electrons. Yeah, and for each of the subshell, there can be more than 1 orbitals. So I'll give an example over at table 4. So for S subshell, there's only 1 type of orbital. So therefore, the maximum number of electrons is 2. But for P subshells, 3 orbitals in total. So 3 times 2, total number of electrons will be 6. So that is why for principal quantum number 2, where you only have 2s and 2p, the total number of electrons that principal quantum number 2 can take will be 2 plus 6, which gives you 8 over here. Yeah, so that explains why. Okay, yeah. And you might also be interested to know that why is it that for P there are 3 different types of orbitals? Because they orientate differently along the axis. Okay, along the x, y, and the z axis. So later on we will elaborate more. Okay, so you notice that for table 4 again, there isn't a need for you to remember them in detail. But what is probably crucial will be the students after knowing or after learning this chapter, you need to know how to sketch the S, P, and the D orbitals. Okay, so later on we'll go through the sketching in a short while. Yeah, I'll just show you how to sketch them out easily. Okay, yeah. So table 5 gives you a summary between the relationship. Of the relationship between the principal quantum shells, subshells, and orbitals. Again, the table is given to you, but there really isn't a need for you to memorize them. Yeah, the reason why there isn't a need for you to memorize them is because, as what I've mentioned earlier on, you can easily predict the total number of subshell in a given principal quantum number. So if the principal quantum number is 3, there will be 3 subshells, and then the 3 subshells, the letter given to them is fixed. It will be S followed by P followed by D, and then in terms of electronic energy level, it will be higher and higher. So S will be the lowest, P in the middle, D will be the highest. Okay, and to differentiate them from the rest of the principal quantum number, we write out the principal quantum number in front of the lettered subshell. Okay, so you do not really need to memorize them, okay, at this stage. Okay, so right now what is important is to learn how to draw the orbitals out. Okay, if you look at learning objective 1G, it is mentioned very, very explicitly that you need to describe the shape of S, P, and D orbitals. Okay, however, the knowledge of wave function is not required. Yeah, so as what I've mentioned at the beginning of section 3, you do not need to know wave functions, which means each of these orbitals is actually defined by a wave function, but there isn't a need for you to learn them. Okay, but of course, if you're interested, please go ahead. Yeah, so there's a schematic representation on the right and the electron density plot on the left. Yeah, so what you need to reproduce during exam is the schematic representation. Yeah, so you should draw them out as though they are three-dimensional. Yeah, so how do you draw them out as though they are three-dimensional? I'll just illustrate it with 1S. Okay, so what I will normally advise the students to do is to first draw the sphere out as a circle. Okay, you don't need to do shading. Okay, just draw the sphere out. Okay, and then after that, you can draw out the axis. Okay, normally we will not advise the students to draw it like this. Okay, usually, because if you draw it like this, it's a bit difficult to tell whether the sphere is three-dimensional or not. So this is normally, we normally will not advise the students to draw it this way. So what you can do is you can just draw it out like this. Okay, like this. Okay, and like this. Yeah, it gives you a little bit of three-dimensional perspective, just a little bit, and that is more than sufficient. Okay, and then you label your axis. Okay, in any way you want. This can be X, Y, and Z. Okay, and of course you can label this as 1S. Yeah, just take note that when you draw, if you are required to draw both 1S and 2S, make sure that your 2S is bigger than your 1S. Yeah, this is quite important. Okay, so again, let me emphasize, make sure your 2S is bigger than your 1S, because your 2S is a more diffused orbital as compared to 1S. So it has to be bigger in shape. And the size matters. Okay, so do remember that. For the p orbital, right, it is, again, not too difficult to draw. Just make sure that you orientate them along the X, Y, and Z axis. So the p orbital are designated as px, py, and pz. So px means along the x-axis, py along the y-axis, pz along the z-axis. Okay, yeah, so what you can do over here is this. Okay, so again, you can use the same logic that I teach you. So for example, if you want to draw pz, to be specific, 2pz, so I will draw a figure of 8 first, a figure of 8 nicely, like that. Okay, and then I will draw in the axis, so like this. Okay, so this is z, okay, like this, and then like this, and then this is x, and then like this. Okay, and this is y. So I am drawing 2pz over here. Okay, so just make sure you have the three, just make sure that your drawing looks a bit 3D, but you don't need to do any shading. Okay, next year when you go on to learn, if you ever take out a H3, you will know that the shading actually represent different things. So do not anyhow shade your orbitals. Okay, yeah, so the electron density plot is given as it is. Okay, yeah, then for the d orbital, yeah, so the d orbital is usually a little bit more difficult to draw for students. So I will go through it a little bit slowly. So again, for the 5 d orbitals, right, they are given the label as x, y, x, z, and y, z. Yeah, I will talk about these 3 first. When they mention x, y, y, z, and x, z, right, they mean that the orbitals are along, okay, the xy plane, the xz plane, and the yz plane. Okay, however, the orbitals do not lie along the axis. Yeah, so just remember this. The orbitals do not lie along the axis. Yeah, so they are just along the plane. Okay, so in that case, I will just show you this drawing. So for example, this is dxy, right? Yeah, so this is actually the xy plane. So you notice that the orbital lies along the plane, but they do not lie along the axis. So they are rotated 45 degrees from the x and the y axis respectively. Yeah, so that is the difference you might notice. And you also notice that the orbitals here are being shaded. So actually the shading is not necessary. We just shade it because the drawing are being imported from CamDraw. Okay, so it comes with the shading. But again, the shading is not necessary. Just remember this. Okay, yeah. Then of course the xz. So this is the xz plane. So the orbitals lie along the xz axis. Yeah. So in order for you to draw the 5 sets of d orbitals, just make sure you learn them in 2 different categories. I thought that would be easier. The first one is to draw dxy, dxz, and dyz, because basically they are just orbitals lying along the plane, but not the axis, 45 degrees from the axis, as what I've illustrated to you over here. Okay, what about dx square minus y square? Okay, this is the interesting one. For dx square minus y square, right, you notice that it is similar to dxy, but it is like dxy rotated 45 degrees clockwise or anti-clockwise. So now the orbitals lie along the plane. Sorry, along the axis, along the x and y axis. Yeah, so that is the difference between x square minus y square and xy. Yeah, do you notice that? Okay, so again, how do you draw it nicely? So again, you can draw it nicely by just drawing out the loop first. So this is the loop, and then I can just draw out the loop like this. Okay, and then after that I can draw out my axis. So this is y, okay, and then this is x, okay, and of course this is the z-axis. Okay, so yeah, so just a sketch will do. I know my sketch is not like fantastically nice or what, but it is perfectly fine. If you can draw a nicer one, please do it. Yeah, but it is important for you to know how to draw them. Okay, the next one that tends to be a little bit difficult for students to draw is the dz square. Yeah, students tend not to be able to draw dz square nicely. So over here I can maybe illustrate how you can draw this out nicely. So I'll just remove the axis for dx square minus y square first. Okay, so the easiest way for you to draw this, right, okay, is really to draw the loop first again. So I'll draw the top loop first, okay, and then I'll just draw out the donut. So the donut will look something like this, and then the other donut will be like this. Okay, so there will be so there will be one below, so you can see that. Okay, so I will just illustrate it out a little bit 3-dimensional if you wish, but if you can't draw it 3-dimensional, it's okay, like this. Okay, because this donut actually covers the bottom, so you can't really see it. And then after you draw it out, then the rest will be straightforward. Yeah, so this is the y-axis, and this is the x-axis. Okay, and then this is the z-axis. Okay, something along this line. If you want to show the axis inside, is fine also, but you don't need to. Okay, so that is how you draw dz square. Yeah, so do practice your drawing, because for the H2 curriculum, as we have shown over here, it is important for the students to know how to describe the shape of the sp and d orbitals, and of course to know how to draw them out. Okay, yeah, so the drawing is something which you need to focus on. Then we have exercise 3.1 over here. So what kind of orbitals must an electron with principal quantum number n equals to 2 occupy? Okay, so you have a few choices, but you know that when n equals to 2, yeah, you can either be 2s or 2p. Yeah, so when I look at all the choices, it's either s or p. So straight away I will choose option B, because it need not be a spherical orbital. Why is it that it need not be a spherical orbital? Because it have a choice. It can either be s or p, right? It may be the electrons might be excited from the 2s to the 2p. You don't know. Okay, so you cannot insist that it must be spherically shaped. Okay, and of course option C doesn't quite make sense lah. Yeah, orbital closest to a nucleus. Okay, yeah, so it's a nonsensical option. A dumbbell shape it represents P. So if you do not choose A, then you shouldn't choose D. Yeah, so the answer should either be S or P. Right. Right, so with that, we'll move on to 3.4, which is really more important. In fact, it might be the most important, which is the electronic configuration. Okay, so electronic configuration is not new for students, for most of you, if not all of you. Yeah, because you learn them in secondary school. Most of you will learn it as the version where you simply indicate the number of electrons in the principal quantum shell. Yeah. But over in H2, you are required to showcase the number of electrons in the subshell. Yeah, so that is when you need a little bit of guidance here lah. Okay, now normally for most of the lecture notes, or even most of the notes, or even the information given in the textbook, right, they will normally teach you this thing called the Aufbau principle, or the building up principle. They will tell you that, okay, the orbital with the lowest energy is filled first. So in this case, you are given the relative energy levels. Yeah, so with this, you know that you fill the 1s first, followed by 2s, 2p, 3s, 3p, and then 4s, right? Yeah, you don't go 3D and then 4s and then 4p. You might be thinking about, why is that the case? Well, because mathematically, right, it has been shown that when the orbitals do not contain electrons, the electronic energy level, right, for a 4s is actually slightly lower than that for a 3D. Yeah, okay, so sometimes you will see a lot of this kind of diagrams lah. I mean, even if you Google it on any university website, they will show you this. Yeah, but how is it that I mean, how can we remember all this? Do we really need to remember how to go about deriving this? Must we really write them out like 1s? I mean, all the s, all the p, and then all the d, and then all the f. Yeah. So my proposal to you is, you do not need to write them out like this. What you need to do is simply just by looking at the periodic table. Yeah. So really, this is what I can share with you, and it's probably the most important thing that you will learn in this particular chapter. Yeah, simply by knowing the periodic table well really allows you to fill in or write out the electronic configuration easily, at least for the first 30 elements. In fact, for the first 38 elements. Actually, in fact, for all the elements. Yeah, you can, unless there are exceptions, if not, you can easily write them out. Okay, how come I'm so sure about this? Okay, I think the first thing I need to share with you is that the periodic table is divided into a few blocks. In fact, in general, 4 blocks. Okay, so over here, right, we call them the S block. This is the S block. Yeah, and then over here, this is called the P block. Okay, then over here, this is the D block. Okay, then of course the one at the bottom, we call it the F block. Yep. So once you know their position, and the periodic table is always given to you in any assessment, right, you can quite easily write out the configuration for any element. Okay, why do I say that? Okay, so I will just illustrate it with an example. Of course, I can easily go and discuss it from the notes. That is not a problem, but I thought that it's easier if I use the periodic table as a platform for you to understand how this Aufbau principle work, or this building up principle work, and you can easily do that on your own. Okay, so I will illustrate with nitrogen, since nitrogen is given here. Okay, so first of all, right, you need to locate the position of nitrogen. So nitrogen is here. Okay, now then the first thing we need to do is we need to move towards nitrogen, but not move like that towards nitrogen. Okay, we need to move along, okay, the corridors of all the atoms before reaching nitrogen. Okay, so in this case, we need to go through 1s. Okay, so this is 1s, right? Correct? Yeah. So in this case, it's 1s2. Why is it 1s2? Okay, so the first number is the principal quantum number, so that is the first period. Okay, then this letter is 1s subshell, right? It's because there's only s subshell for the first principal quantum number. The 2 here denotes the number of electrons in the subshell. Yeah, so hydrogen, helium is the second element in the first period, so that will be 2 electrons. Then next, okay, we need to move across period 2. Okay, so we have lithium and beryllium. So lithium and beryllium are in the S block, right? So in this case, we are looking at 2s, right? 2s, right? We are filling up 2s. Remember the Aufbau principle? Yeah. So we are looking at 2s. So how many electrons are there? Lithium 1, beryllium 1. So 2s2. Yeah. And then nitrogen is the third element in the p block in period 2. So in this case, still period 2, 2p. So the number of electrons will be 3 because it's the third element in p block. So 2p3. Yeah, so in this case, the electronic configuration of nitrogen will be 1s2, 1s2, 2s2, and then 2p3. Yeah, so this is how we can go about using the periodic table to write out the electronic configuration. Okay, right? So right now I will just erase all this because it's really very messy. Yeah, then after I erase them, you can try them out on your own again. Okay, so I will just illustrate using another example. Okay, so that you can see for yourself. Okay, so again, let's say I want you to write out the electronic configuration for, let's say, aluminium. Okay, so again, this is 1s, so yes, 1s, so it's 1s2, right? And then this is 2s2, right? Okay, and then we are going across period 2 all the way until neon, so this is 6 elements, so 2p6. Yeah, so remember, this is S, and then this is 2p, and then this is 3p, 4p, 5p, 6p. Yeah, so that is how you can easily derive the electronic configuration by just moving along the corridors of the periodic table. Okay, and then after that we come to here, this is 3s2. And then for aluminium, 3p1. Yeah, so the electronic configuration of aluminium would be 1s2, 2s2, 2p6, 3s2, 3p1. This is the full electronic configuration. You can actually write the short form out if the question allows you to do so. So 1s2, 2s2, 2p6, I can write it as a short form. It has a neon configuration, and then it will be 3s2, 3p1. Yeah, okay. Yeah, so I illustrated to you how you can use the periodic table to help you derive the electronic configuration. Yeah, this method can only help you to derive electronic configuration of elements, but it cannot help you to identify the exceptions. Okay, so there are exceptions along the way which we will discuss later on. Yeah, so you don't really need to remember the Aufbau principle. You don't really need to remember figure 10. Again, you don't really need to use the figure 11 as the mnemonics. You can simply use the periodic table. Okay, for the Hans rule of multiplicity, what does it mean? So okay, so each orbital must be singly occupied first before they are paired up. Okay, so yeah, this is pretty important. So I must occupy them singly first before pairing can occur. Yeah, so this is the Hans rule. Yeah, so for example, okay, so what do we mean? So for example, just now we talked about nitrogen, right? Yeah, so for nitrogen, the electronic configuration was 1s2, 2s2, 2s2, 2p3, correct? Yeah, so the 2p3, because p has px, py, and pz. Yeah, so the order would be I will first have to fill all the p orbitals up singly before I pair them up. So that means that for oxygen onwards, right, oxygen will be 1s2, 2s2, 2px2. Either px2 or py2 or pz2, it doesn't really matter. Yeah, so this is the Hans rule. So because the orbitals are degenerate in terms of energy, okay, because all the orbitals in the subshell are degenerates in terms of energy, so you have to fill them up singly first before pairing can occur. Okay, so that is what Hans rule is trying to tell you. Okay, so for rule number 3, that is the Pauli exclusion principle. Okay, this is very important. Okay, so for the Pauli exclusion principle, it says that the orbital, right, cannot have more than 2 electrons, and these 2 electrons must have opposite spin. Yeah, so earlier on, I think I made a little mistake in front. I think earlier on, somewhere here, I mentioned about where you can identify the position of the electrons with 4 unique quantum numbers, right? Yeah, so I think I accidentally say Hans rule. So what I'm referring to is actually the Pauli exclusion principle. Yeah, so you notice that for the Pauli exclusion principle, for at the H2 level, they basically just tell you that the orbital cannot hold more than 2 electrons in the orbital, and they must have opposite spin. This is the Pauli exclusion principle that you learn in terms of an explanation at the H2 level. If you move on to the university level, right, they will tell you that no electrons can have the same 4 principal quantum number. Okay, then over here you might be thinking, what is the meaning of cannot have the same 4 principal quantum number? Okay, so you notice that for an electrons in the orbital, so for example, I have 3px, for example, if they are being paired up, okay, they will have the same principal quantum number 3. Okay, correct? Yeah. Because they are in the p subshell. So again, the second principal quantum number, if you remember what is it called, is the azimuthal principal quantum number will be the same, right? And because the orientation is px, so the magnetic quantum number will be the same. Yeah, but the spin is different. The fourth quantum number is known as the spin quantum number, which is, of course, as I mentioned, is not in your syllabus. Yeah, so it will have 3 similar quantum numbers, but the fourth one, which is the spin quantum number, will be different. Yeah, so that is the Pauli exclusion principle, at least at the undergraduate level. Yeah, no 2 electrons can have the same 4 or can have the same 4 sets of quantum numbers. Yeah, it will be differed by at least the spin quantum number. Yeah, this rule cannot be disobeyed. Just remember this. If you want to understand why it cannot be disobeyed, then you have to read up on quantum chromodynamics. Yeah, understand about the up, down, cos, etc. Yeah, but we will not go into details in this case. Okay, so this is the Pauli exclusion principle. Just remember this, right? Okay. And then we have exercise 3.2, which is a word example. I don't think you need me to go through them, but of course, in your own rights, please work them out on your own. Understand how the electronic configuration are written, and how the electron in a box diagram is written as well. Yeah. So do remember that whenever you show electrons or a pair of electrons in an electron in a box diagram, right, they have to have opposite spin. Yeah, do remember that. Okay, and of course earlier on I did mention that chromium and copper are 2 exceptions. Okay, I didn't mention that they are exceptions, but I mentioned that there are exceptions. Okay, so these 2 are exceptions. So based on what you heard from me earlier on, so maybe I can just go back to this again. I can just erase this first. Okay, we'll use chromium as an example so that it's easier for you to understand what I'm talking about. Okay, so let's say I want you to write out the electronic configuration of chromium, for example. Okay, if you follow what I did earlier on, you know that, okay, so it's 1s2, 2s2, 2p6, so I'll just write it out first. 1s2, 2s2, 2p6, okay, 3s2, 3p6, okay, so 3s2, 3p6, okay. Now, here is 4s2, right? So we have 4s2. After filling with electrons, they will have a higher energy levels. Do remember this. Okay, so you'll be over here. And then this is followed by 3d4. 3d4. Yeah. You will have submitted this as the answer. Am I right to say that? I mean, if you go by what I've mentioned to you earlier on, how do you actually use the building up principle? How do you incorporate Hans rule into your filling and Pauli exclusion principle as well? Yeah, but chromium is actually an exception. Its electronic configuration is not what I've written. Its electronic configuration is actually 3d5-4s1. Okay, so it's a bit unique. So it's 3d5-4s1. Yeah, why is that the case? Okay, so you can actually understand more by reading out further, but it has got to do with the exchange energy. So you notice that when we write it as 3d4-4s2, right, the 4s orbital is filled, but 3d4 are singly filled. But for 3d5-4s1 all of them are half filled or singly filled. Yeah, so in terms of a concept known as the exchange energy, having the 3d and the 4s orbital half filled, right, will put it in a more stable electronic configuration as compared to having it as 3d4, 4s2. Yeah, so again, if you need more details, please go and read up on them, and then these are important details which I think we will not be able to cover at the H2 level. Okay, same as copper. So for copper, the electronic configuration, the preferred electronic configuration is 3d10 4s1 instead of 3d9 4s2. Yeah, so these are the two exceptions which you need to know at the H2 level, right? Okay, then okay, so we'll move on to the next bit, and then when writing electronic configuration of cation, you have to first write the electronic configuration of the atom and then remove the number of electrons equal to the positive charge. Yeah, so in this case, you have to start from the one with the highest electronic energy level. Okay, so what do I mean here? So for example, the electronic configuration for copper, okay, is written as it is valence electronic configuration 3d10 4s1. Yeah, so for copper 2 plus, the electronic configuration will be blah 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 3d9. Okay, so do remember this, because if you remove them wrongly, your electronic configuration for cation and anion will be written out incorrectly. So do remember that. Okay, and then of course when you add electrons, you add them into the valence orbital as well. Yeah. Okay, so for exercise 3.3 as a work example, so for example, for unipositively charged sodium, the electronic configuration for the atom is 1s2, 2s2, 2p6, 3s1. So if you remove electrons, you'll be removed from 3s. Okay, so therefore the electronic configuration for sodium plus is 1s2, 2s2, 2p6. Yeah, essentially it has the neon electronic configuration. Okay, for iron 2, right, when you write them out as the argon configuration 3d6 4s2. You notice that you do not write them out as 4s2 3d6. Yeah, because when electrons are being placed into the subshell, okay, the 4s orbital, right, has a higher electronic energy level. Yeah, simply because of the fact that it has principal quantum number 4, so it has to be written out as the valence orbital. Yeah, so when you remove electrons, you remove from the 4s and not the 3d. Yeah, so therefore for iron 2, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Okay, so again for chloride, everything else same. I think that is not too difficult, not too inspiring, but when you add electrons, you add it into the 3p subshell. Okay, so electronic configuration for chloride will be 1s2, 2s2, 2p6, 3s2, 3p6. Okay, yeah. Then right, so for exercise 3.4, okay, so question is, which of the following particles would on losing an electrons have a half-filled set of p orbitals? So again, what is the best way of doing this question? Yeah, is to write out the electronic configuration. Yeah, so electronic configuration for carbon is 1s2, 2s2, 2p2. Okay, for nitrogen, 1s2, 2s2, 2p3. Oxygen, oxygen will be 1s2, 2s2, 2p4. Okay, so over here they said on losing an electrons have a half-filled set of p orbitals. Yeah, so they are talking about these particles. They are not talking about their elements. Okay, so in this case, I have to write it as C minus. So for C minus, the electrons will be, the valence electrons will have 3 in the p subshell, so 2p3. Okay, for nitrogen minus, instead of 2p3 here, it will be 2p4. Okay, and then for O plus, instead of 2p4, it will be 2p3. Okay, and then of course I need to write for O minus, that will be 1s2, 2s2, 2p5. Okay, now what I'm going to do is I'm going to remove an electron. So if I remove it for C minus, I'll remove it from 2p3, so I'll be left with 2. For N minus, I remove it, left with 3. O plus, remove, left with 2. O minus, remove, left with 4. Yeah, so the only one with a half set of p orbital is actually N minus. Okay, so the option will be B. Okay, so you have to be a little bit careful sometimes when you are dealing with MCQ because they can be a little tricky. Okay, yeah. And then electronic configuration and periodicity, I think I have jump started a little bit because I thought it is actually easier for you to look at electronic configuration by simply looking at the periodic table. Okay, so as I mentioned earlier on, if you are looking at period 2, we are filling up 2s and 2p subshells. Okay, so this is actually what this portion is trying to tell you. Okay, so since I've jump started, I do not need to discuss too much from here. Okay, so again, I need to emphasize on this. Do not memorize this thing because there isn't a need to. You can simply whip out your periodic table and then just count. It's as simple as that. Okay, so do not memorize it. It is totally non-essential. Okay, what about transition metal? So what exactly is a transition metal? Okay, so this will be the first time you're hearing this, and then the last time you're going to hear this will be next May. So 2024 May. So by definition, transition metal is a d block element that form one or more stable ions with partially filled d subshell. So remember this, one or more stable ions with partially filled d subshell. Okay, so therefore by definition, scandium and zinc are not considered transition element because for scandium, it only forms as scandium 3+, which have D0 configuration. Okay, for zinc, the only stable one is zinc 2+, which have a D10 configuration, so they are not considered as transition metal. Okay, yeah, so again, if you are not super sure about this, it is perfectly fine. It will be revisited in JC2, okay, sometime in 2024 May, so don't worry about it. Right, for exercise 3.5, that's the final exercise for section 3. Okay, which of the following corresponds to the configuration of the 3 electrons of highest energy for ground state of an element? Group 13. Okay, now some of the keywords. 3 electrons are the highest energy element in group 13. Okay, now first of all, right, we need to understand group 13. So I need to go back to the periodic table. Okay, I need to erase a lot of these things because it's just a bit messy. Okay, just really messy. Okay, so group 13, we are looking at this group 13. Okay, now for group 13, we have boron here, right? So what is the valence electronic configuration for boron? 2s2, 2p1. Am I right? Okay. How about aluminium? 3s2, 3p1. How about for gallium? 4s2, 4p1. These are ground state electronic configuration, which means the electrons are not being excited. So do remember this. Okay. Now, if we go back to our options here, they wanted the highest energy for ground state of element from group 13. Okay, so definitely A is out because A we are looking at group 1. Okay, B is out. Why? Because we are looking at one of the s electrons from boron being excited to 2p. Yeah, but I don't think that is going to be the highest because of the other choices. Okay. Again, we are not looking at this because this is 3p3. Again, some excitation is needed. So they are not ground state. So again, it's not correct. So the only option we are left with is D, which correspond to gallium, 4s2, 4p1. Okay. Yeah. So that is the end of exercise 3.5. I hope you understand what's going on. Okay, so the next portion or the next lecture we're going to discuss is actually from section 4 onwards on periodic trends in atomic and ionic radii.